Hi! Now that we have seen the singular value decomposition, we can consider also one of its most important applications, principal component analysis. This application falls a bit at the interface between linear algebra and statistics. As such, you will need some understanding of the notion of variance and covariance to understand the power of the technique. Roughly speaking, when we try to analyze data, we are dealing with two main problems. The first problem is caused by what you might call noise, determined by the level of uncertainty in our data producing mechanism. And it is not what principal component analysis is meant to deal with. The second problem, however, is redundancy. When we don't understand the important features of a problem and decide to analyze it by collecting data, it is unlikely that we will align our data collection exactly with the most important aspects of the problem. As such, we will likely collect data which is covariant and therefore doesn't give us new information. Principal component analysis allows us to determine what the most important dimension is in our data. And so we may focus on those. The technique will become best apparent by considering an example. So let's consider a physical setup, where we actually already know the dynamics, but we see how we might rediscover that dynamics from data. In particular, we'll consider this simple mass on a spring system. If we pull the mass directly downward, away from equilibrium, we know that it will simply oscillate with some damping factor in the up and down direction. In particular, given the spring constant, mass, and damping factor, we know the differential equation governing the motion, and we know the solution. This is made especially easy since we know that the motion only takes place in one direction, namely up and down. Now suppose we don't know any of that and would like to determine it by collecting data. In particular, we will set up 3 cameras to make pictures every 10th of a second. Since we don't know anything about the dynamics, we will make sure to set the cameras up at various different angles. Let's say we run the experiment for 10 seconds. The result of this experiment will be 6 vectors with 100 components each. Indeed, each camera will provide 2 of these vectors in the following way. We consider a coordinate system for the camera frame. Note that this means we have 2 coordinates per camera, x and y, since the picture is 2-dimensional. Per 10th of a second, we record the location of the mass in the camera frame. We note the x-coordinate in the corresponding component of the x-vector for that camera, and we note the y-coordinate in the corresponding component of the y-vector for that camera. So for instance, the 4th component of the x-vector for camera B will be in the x-coordinate for the mass in the 4th picture made by camera B. Now, it would be strange to pick the coordinate frame in each camera frame completely randomly. So indeed, what we will do is make sure to pick an orthogonal coordinate system such that the average of the components of each vector is 0. In other words, we recalibrate by putting the origin of our axes at the point with x-coordinate equal to the average x value over all pictures and the y-coordinate equal to the average y value over all pictures. Of course, we do this for each camera separately. The upshot is that now we have 6 vectors of data, each of which has 0 as the average of its components. But of course, this data will be heavily correlated. Indeed, we know that we do not need 6 vectors to describe the dynamics of the system. We only need 1, since the dynamics are one-dimensional. To figure out how, we may consider the variance and covariance. To get an estimate for this covariance, we consider the sample variance and covariance, which are very neatly expressed simply as scaled versions of the various vectors. Indeed, 1 over 99 times the inner product of a vector with itself provides the sample variance, and 1 over 99 times the inner product of a vector with another vector provides the sample covariance between those 2 vectors. Things become even simpler if we consider the matrix X, whose rows are the observation vectors. In that case, we simply consider the matrix X times X transpose. This is a symmetric matrix whose diagonal entries are 99 times the sample variances and its off-diagonal entries are 99 times the sample covariances. If our data were free of redundancy, we would get a diagonal matrix, since all covariances would be 0 and one of the diagonal entries would be a positive number while all others would be 0, since there is only movement in one direction. Of course, this would correspond to the situation where I set up just one camera and made sure to line up its x or y direction exactly with the up or down axis. Of course, without prior knowledge about the system, we wouldn't do this. What we can do is consider a different reference frame for the data that we have acquired. If we consider the singular value decomposition of x, we find that x equals u times sigma times v transpose, with u, v, and sigma having the properties associated with a singular value decomposition. In particular, u and v are orthogonal, and sigma times sigma transpose gives us a diagonal matrix D, which has the eigenvalues of x transpose times x on its diagonal in decreasing order. The new reference frame is provided by the orthogonal basis, which provides the columns for the matrix U. So our new data matrix will be A, which equals U transpose times X. We have now replaced the data matrix X by the matrix A, which gives us the same data, only in a different reference frame, related by the change of basis given by the matrix U transpose. Let's compute the covariance matrix related to the data in these new coordinates. We find 1 over 99 times A transpose, which equals 1 over 99 times U transpose times X transpose times U. We may now plug in the singular value decomposition for X to find that 1 over 99 A transpose equals 1 over 99 times U transpose times U times sigma times V transpose times V times sigma transpose times U transpose times U, which is simply 1 over 99 times sigma transpose, since both U and V are orthogonal matrices. The matrix sigma times sigma transpose is of course just the diagonal matrix D that has the eigenvalues of x transpose times x on the diagonal in descending order. In particular, we now see that the covariance of our new data matrix is 0, and as an added bonus, the rows of A give us the data ordered from data with the most variance to data with the least variance. In our example, only the first row will be important, although some variance may still appear in the lower rows due to noise. The upshot is that principal component analysis uses the singular value decomposition to determine the dimensionality of our problem. Moreover, it provides the data in a new frame of reference that removes redundancy and orders the data according to variance. Of course, the example of the mass on a spring was chosen to show the idea of principal component analysis in a situation where we already know the answer. To wrap up this lecture, let's have a look at an actual application of principal component analysis. We'll have a look at the technique of so-called eigenfaces. This is a technique used in facial recognition, where faces are recognized by looking at their decomposition into eigenfaces, the principal components. And of course, only looking at the most important eigenfaces, which are the ones with the highest variance. The starting point is a database of a bunch of pictures of people's faces. Usually, you will want multiple pictures per person. What we want the program to do is be able to tell us who we are looking at if we provide another grayscale picture of a face of a person that is in the database. The first thing we should want to do is figure out how to turn pictures into vectors of data. Each pixel in the picture will have some value assigned to it between 0 and 1, going from black to white. We turn the picture into a vector by simply letting the first components of the vector correspond to the first row of pixels in the picture. Then we let the second set of components in the vector correspond to the second row in the picture, and so on. We encode each picture into a vector this way, and so our entire database can fit into a matrix X. Each column of this matrix will be the vector corresponding to one of the images. This means that each row in the matrix provides the grayscale value of a particular pixel in each picture. We are interested in how these values vary from person to person. So to start with, we will want to consider the values of pixels as deviation from the average value. In other words, we want to take the average picture, the picture obtained by averaging the grayscale values of each pixel over all images, and subtract it from each picture in the dataset. We obtain this way the matrix A. Now, let n be the total number of pictures. Then the matrix 1 over n minus 1 A times A transpose is exactly a symmetric matrix where the diagonal entries give the variance in individual pixels and the off-diagonal entries give the covariance between pixels. Of course, comparing faces pixel by pixel is an absurd tactic, and indeed we would expect a lot of redundancy. For this reason, we apply principal component analysis, in other words, the singular value decomposition, to change bases to the matrix B, which equals U transpose times A, where U is the matrix of left singular vectors in the singular value decomposition of A. The covariance matrix for B will be diagonal, and the diagonal entries will be in decreasing order. Note that the new basis of vectors can be viewed as pictures in their own right. The first basis vector corresponds to the most meaningful way in which a face can deviate from the average face. The second basis vector is the second most meaningful way, and so on. These pictures are what we call eigenfaces. Usually, you'll pick some cutoff and only consider the first so many eigenfaces, since the rest are much less important in your facial recognition. On the slide, you see an example of some eigenfaces for a particular dataset. The rest of the function of the program would be to look at the principal components of our given picture in the eigenface basis and then compare it to the principal components in the pictures, or rather average pictures, of each person in the dataset. The person whose vector of principal components is closest would then be selected. Of course, there's much more to be said about this very interesting application of linear algebra, but this course is not the right venue for such a discussion. Hopefully, you have been convinced of the powerful application of the singular value decomposition and are already looking for a deeper dive into the topic. For now, make sure to make the exercises for this lesson.